Hello everyone, I'm Alexander Trujillo, currently studying a specialization in high-performance computing in Italy, and my project during this summer is called Performance Comparison and Regression for XDM. The project looks forward to integrate benchmarking scripts for the Xtm software using a comparative approach. The final desired result should point changes in performance or scalability for different cases under some conditions. Here, Bash and R scripts will give the PDF with user-friendly visualization of the benchmarking. Before moving on, a little bit of background would be really helpful. So let's start talking about the XDM software. It is a numerical simulation framework implemented using C++. It performs calculations using the extended discrete element method, a method which, besides describing the dynamics of granular material, also obtains additional properties of the conglomerate of particles, as the thermodynamic state, stress, etc. Even could be coupled with computational fluid dynamics solver as an open form. At the left, we can observe a digital twin of the blast furnace, which is one of the sample cases to benchmark here. XDM has many computational phases, but only few are the most important ones, and usually those take the most of the execution time total. So let's start with the broad phase, that is a preliminary approximation that builds a list of particles pairs that can potentially interact with each other. To make a fast calculation, these particles are represented by bonding spheres. Then there is the narrow phase that now performs a precise contact detection using the actual shape of the particle, and then calculates the actual distance between these. Then the applied dynamics model phase is related to solve the dynamic model that is defined for each particle, like impact, bonding, rolling, and as well it calculates the contribution of the interaction to each particle involved. So before explaining the communication phase, an important concept is the domain decomposition, which is how the workload is distributed throughout the compute nodes. The spatial location is divided in cell grids, which could contain a variable number of particles at any time. Then these cells will be grouped in subdomains and then assigned to certain compute node. The last process varies depending on the decomposition algorithm, but in a broad sense it converts these cells into nodes that belong to a graph and performs the partitioning according to neighbor relationships with the objective of balancing the workload and minimizing the communication. Once the decomposition is done, we create the boundary of another compute nodes as these need to share information of the particles constantly in runtime. These cells are called ghost layers. Now we will proceed to list the use case for any simulation result, taking a comparative aspect for previous executions. By means of Bash, R, and the Slammer scheduler in the cluster, the benchmarking results will be obtained in an automated way. Here are the results obtained by means of these scripts, and here it's important to note that I was using the cluster ION of the University of Luxembourg, which has 318 compute nodes and a fast infinite band network of 100 gigabits per second. The case used for this example report is the simulation of a blast furnace cherry. Here is a video of the simulation case. So let's start with the strong scalability report. These plots are the following. It will show the time execution evolution according to the number of compute nodes, as well as the speed up plot. The R script loads and transforms the data generated by the XDM, and once done this, it will obtain the time execution for the different phases. It will create a speed up plot for each category and focusing on the most relevant. Also, it will create a heat map of the efficiency across different categories, as well as a steam graph of the proportion execution time to observe the evolution and changes in importance for different categories when more computes are added. The feature plots for the weak scalability report are similar for the strong scalability case, but here it is required by the script to explicitly state the number of particles or size used for each run. As well, for the size performance comparison and complexity characterization, the analysis identifies the complexity of the measured computing time for the principal categories. Besides, it creates a heat map for the scaling factor, checking as a reference a linear increase. If it is scaling in higher order, it will reveal a deficiency on the category. So here, for example, we can see here the code complexity analysis for the applied dynamics models, which follows a linear trend, That makes sense because it's related to the number of particles. Now the performance regression. Here we compare the performance changes between a reference and a different software versions. It shows the drop or rise in percentage for the total execution and for different computational phase, as well as a heat map pointing out the worse and better performance category for each version. Now, for this report, it will create for the decomposition performance comparison individual evolution plot for each decomposition compared to a reference. So in this case, for example, the ORB decomposition, which we can see here how different algorithms could create different performance for each run. So we can see here this heat map pointing out which is the worst performance and the better performance according to different decomposition. To conclude, now XDEM has additional tool that will help to the developers to keep track of the improvement over time. Now this will be attached to the XDEM continuous integration, and even users could test with a little version of the original work to see which is the best decomposition or version for their project. Thank you very much for your attention.